we also solved problems and should just recall some relationships. So it is d by e, d by e, that is flux density to field intensity. This is what the first relationship we have discussed. Okay, and for line charge, for line charge, your d is equal to rho l by 2 pi r into a r cap, and for surface charge, the flux density is given by rho s by 2 a n cap, and for volume charge, d we have discussed. It is nothing but rho v into dv divided by 4 pi r square into a r cap. So this is what we have discussed yesterday. Okay, and that is nothing but if you know the expression for field intensity, then you can solve for the flux density. So they are actually same. That means the field intensity and the flux density will be in the same direction. Will be in the same direction. So now we shall move on to one more concept. Okay. So just check out here. So I am having a closed surface like this, and having a charge like this q, and I'm having a same closed surface, and I'm having a charge like this, and again the same um, closed surface. So here, so this is what we mean to say sphere. So here, a point charge is inside this sphere. Okay, point charge of q coulomb, and here line charge of q coulomb is inside this sphere, and surface charge of q coulomb is present inside this closed um, sphere. Okay, so and what exactly the charges or the lines of um, forces emanating out of the sphere, it is equal to what? Phi. Okay, that is equal to q. So phi is equal to q here, and here a line charge is being enclosed by this closed sphere. So therefore the flux leaving the sphere or the surface of the sphere is equal to again q. This is q, sorry, this is q, and this is also q. And for the surface charge, again in this case the flux lines leaving the surface of the sphere will be equal to again q. So what you can observe here, the sphere is enclosing different types of charges. One is point charge, line charge, and surface charge of same quantity, that is q coulombs. And as a result of it, there is some flux lines crossing the surface of the spheres like this. Okay, that flux lines is same as your charge, and here also the surface of sphere, so you'll be able to feel that flux lines crossing the surface, that is due to line charge, and here surface charge of q coulombs like this. Okay. Yes. The total flux radiating outwards from the surface of the sphere remains same. Okay, that is Q. So this is what a regular shaped sphere. For example, if you have an irregular shaped item like this, okay, so like this, an irregular shaped item like this, and if you have again a point charge, and if you are having a line charge of q coulomb, and if you are having a surface charge like this, which is enclosed by the irregular shaped surface, closed surface, again the total flux will be same as Q. Here also total flux will be same as Q, and here also the total flux emanating from the surface of the irregular shaped body, it is same as Q. So what you can infer from here? So any closed surface which is enclosing some charged particles, from that the total flux crossing the surface of an irregular object remains equal to what? The total charge Q. Okay, so it is from the Faraday's experiment. So what you have to infer here, so irrespective of the shape of the um, body which is enclosing the charge, the flux radiating will be equal to your total charge enclosed by the body. Okay, so this is nothing but Gauss law. This is nothing but Gauss law. So what Gauss law states, so I'll just write it here. Gauss law. The electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So what is that Gauss law? So flux leaving the surface will be equal to what? Total charge enclosed by that surface. So the body can be anything. It has to be what? Closed surface. That's all. It has to be what? Closed surface. The electric flux passing through or radiating through the closed surface will be equal to what? The total charge enclosed by that surface. So how to mathematically represent that one is the next question. Okay, just follow me here. So let me have some irregular shape of the surface like this, and let me have a small area here. Let the point be on the small surface as B, and let the charge be Q. Okay, so the small surface I am considering it as ds. So as a result, what will happen? There will be some flux density due to this charge Q. Okay, that density is given by d vector. Okay, so what is that I'm having? I'm having a closed surface which is enclosing a charge Q. In that closed surface, I am considering a small surface ds, and the point P is on that small surface. Okay, so due to this charge Q, I am having flux lines crossing that surface. Okay, yes. So also I will mark the perpendicular at the small surface like this. So this is my perpendicular AN cap at P. Okay. So this is creating one angle theta between the flux density and the perpendicular or normal to the point P. Okay. So there is some power fluctuations. Please bear with me. So what is that I am having now? I am having a closed surface that is irregular in nature, and I'm having a Q which is enclosed by that closed surface. I'm having a ds small area, okay, and an is the unit vector which is normal to the surface ds at point P. So what exactly we are interested in doing it? We are required to find out the total flux radiating the radiating outside this closed surface. Okay, so that is I wish to find phi here. What exactly the phi here in this irregularly shaped surface? We know that phi will be equal to q, but I need to establish a relationship. Yes, so I'm just establishing a relationship now. So the flux density at point P is d vector, and as I have said, it is making an angle theta with the normal direction at point P. So d phi, d side, sorry, it is d psi is the flux passing through the surface ds. Okay, the flux d psi is the flux passing through the surface ds. Okay, which is nothing but product of the surface area, okay, into, that is the product of the surface area and the flux density, the flux density, so which is normal to the surface ds, which is normal to the surface ds. Okay, so just follow me here. So as we have discussed yesterday, the flux lines will be normal to the surface. So I am just establishing relations here. So the flux lines have to be what? Perpendicular to the surface of consideration. So here dn. So dn is equal to magnitude of d into cos theta. Am I right here? So this is a normal vector at P. So I just have to find the vector component of this flux density d. So that is equal to what? D cos theta. Therefore, my expression for d psi becomes, okay, ds into d into cos theta. ds into d into cos theta. So this is what, so I have got. So I just carry forward this equation onto the next slide. So your d psi is equal to d cos theta into ds. Similarly, d into ds into cos theta. Okay. So how this looks like? Can somebody tell me how this looks like? Yes, very first class.
Dot product.
Exactly. So it is nothing but the dot product. of two vectors. So this is one vector and this is another vector. So just take the dot product of these two, you will be getting the total flux. Okay, so ds vector. Okay, so therefore, if you want to find the total psi, so you will have to integrate this d psi, okay, along the surface, okay, and take the cross the dot product here, and this is equal to what? The closed loop integral, like this. Okay, so this is nothing but closed surface integral for closed surface, and it is called closed surface integral. Okay, and the closed surface is called Gaussian surface. Is called Gaussian surface. So irrespective of the shape of the surface, the flux passing through the surface is the total charge enclosed by the surface. Okay, so what is that you have to understand through this one? The Gauss law is very particular in saying that the flux leaving the surface will be equal to the amount of charge present inside the surface. That is a statement of Gauss law. Okay, and it has to be what? A closed surface, and it can be of any shape. Okay, and it can enclose any kind of charge. That it can enclose a point charge, it can enclose a line charge, it can enclose a surface charge, it can enclose a volume charge. Okay, so the closed surface is known as Gaussian surface. Okay, yes. So what exactly the specialities of Gaussian surfaces? Okay, so it is nothing but a closed surface, and at each point of the surface, your d vector is normal. Is normal. D vector is normal to the surface or tangential to the surface. Okay, and also d is constant over the surface. Okay, the surface might be irregular. Surface is irregular in shape. It might be irregular in shape, but it should be large enough to enclose the entire charge. Okay, so this is what the characteristics of any Gaussian surface. So, and what are the limitations? What is the limitations of this is the characteristics and limitations of Gaussian surface. So it is limited to symmetrical problems. What do you mean by symmetrical problems? Symmetrical problem is nothing but your D has to be normal. D has to be normal. So Gauss law will not be applicable when the flux is not normal to the surface. Okay, so it can only be applied to the closed surface. These are the two limitations. So it is applicable only for closed surfaces, and that is it is limited to the closed surfaces, and it is applicable where D is normal to the surface. Okay, everywhere. So this is how the Gauss law is applicable in the system. Okay, we will make use of this Gauss law in the applications part of this chapter. Okay, applications of Gauss law. So we shall come back here. Yes, any doubts up till this point, ladies and gentlemen? If you have got any doubts, please raise it on the chat box.
Sir,
Yes.
what's the second point of the characteristics?
Sorry.
Characteristics of Gaussian surface. Second point.
Second point, D is constant over the surface. That means, so the flux density should be constant at every point on the surface where the vector D has to be perpendicular to the surface. So in some surfaces, on some surfaces, the D will not be constant. The D will be varying, and on some surfaces, the D will not be normal to the surface. Okay, so this is the distinction between the constant as well as the normal of the D. The D has to be constant, and D has to be what? Perpendicular to the surface. Okay. Yes or no?
Sir,
No.
hello, sir.
Hello.
Sir, can you explain once the limitations of Gaussian
Limitations.
surface? Yes, sir.
Yes. Limitations. It is applicable only for symmetrical systems. Symmetrical systems. Symmetrical systems means the D is normal. The vector D is normal to the surface. When D is not normal, that system is said to be unsymmetrical. Okay. So Gaussian surface means what? You will be getting the lines of forces or flux lines which has to be what? Perpendicular to the surface. Which is when it is not perpendicular or when it is not normal to the surface, then you can claim that it is an unsymmetrical system. So you will have to find a symmetrical system. Okay, and it is applicable only for closed surface. It is applicable only for what? Closed surface. Okay, that means um, the charges has to be completely enclosed. The charges has to be completely enclosed by the surface. Okay, these are the two distinct limitations. There are many limitations, so we shall see when it is applied to the engineering extent. Okay.
Okay, sir.
Yes. So now let us solve one problem here. Here the flux density is given. The flux density D vector is given as R by 3 into AR cap nano coulomb per meter square. Okay. So the flux density D vector is equal to R by 3 AR cap nano coulomb per meter square. So you will have to find E vector at R is equal to 0.2 meters. Okay, and you will have to find the total flux psi. Okay, at R is equal to 0.2 meters. Okay, sphere of radius R is equal to 0.2 meters, and you will have to find total charge at R is equal to 0.3 meters. That is sphere of radius 0.3 meters. Okay, so this is the question you have been given. So you will have to find intensity at when R is equal to 0.2 meters you will have to find the total electric flux leaving the sphere of radius r is equal to 0.2 meters, and you will have to find the total charge of the sphere r is equal to 0.3 meters. So let me solve this problem. Okay. Yes. So we have got a relationship now. So what is the relationship between E and D? E is equal to D by epsilon naught. We know the value of D directly, R by 3 into epsilon naught into AR cap. R value have been given. Substitute the value, you will get the answer. It is 0.2 meters. Divided by, oh, I think I lost it. I have lost the file. I could not save it, so I have lost the file. Hmm. Did you people notice the problem?
Yes, sir.
Yes. Then it's okay. Or else I will just write once again. I could not save it. So D is given for you. It is R by 3 AR cap nanocoulomb per meter square, and you will have to find E at R is equal to 0.2 meters, and you will have to find psi at R is equal to zero point 0.2 meters. You will have to find Q at R is equal to zero point 0.3 meters. Okay. Yes. Now let me use a standard relationship. E is equal to D by epsilon naught. D is given R by 3 AR cap. It is nanocoulomb. Nanocoulomb is into nano, or else I'll write as a 10 power minus 9 divided by epsilon naught. So if you substitute, you'll get it as 7.52 AR cap volts per meter. This is the first solution. Second solution, are you able to follow?
Yes.
Yes. Yes. Next solution, I want to find psi, that is equal to closed loop integral d vector into ds vector. Okay. So d vector is given. You are required to find ds vector. Ds vector is the surface area of the sphere. It is given to be r square into sine theta into d theta into d phi into ar cap. Okay. So ar cap is the normal. Okay, is the normal. So the surface area is given to be what? R square sine theta into d theta into d phi. It is the um, area of the sphere, which is taken to be as ds. Okay, using that you can find out d vector into ds vector. So r by 3 into 10 power minus 9 into, okay, ar cap. This is d vector dot product of r square into sine theta into d theta into d phi into ar cap. Okay, so what is ar cap into ar cap? Is dot product.
1.
1. So it is r cube by 3 into, okay, sine theta into d theta into d phi. This is d vector into ds vector. Okay, now I'm required to find out phi, closed loop integral d vector into ds vector, that is equal to, so there are two integrals now, one for phi and one for theta. So phi is nothing but azimuthal angle, so varies from 0 to 360 degree. Theta is the half angle, varies from 0 to pi. So therefore we'll be having two integrals. Phi is equal to 0 to 2 pi, theta is equal to 0 to pi, r cube by 3 into sine theta into d theta into d phi. If you solve for this, you will be getting 4 by 3 pi r cube nanocoulomb. 4 by 3 pi r cube nanocoulomb. What is 4 by 3 pi r cube?
Volume of sphere.
Exactly. It is nothing but what volume of the sphere. That is what we have derived now. Okay. So volume of the sphere. So if you know Q, 4 by 3 pi r cube, you can find Q at r is equal to zero point 0.2, and also you can find Q at r is equal to 0.3. So this is the how you find the total charge enclosed in the sphere. Okay. Yes. Any doubts here at this point?
No, sir.
Okay. So I just lost the file. I could not save it. Okay. Yes. Now one more problem. So shall I stop at this point? Next 12:40 is the next class, right?
Yes, sir.
Whose class?
Yeah, that
Sir,
one.
Manjunath, sir,
Yeah.
Max.
Maths. Okay. Okay. I will stop at this point. Uh, Tomorrow we should discuss again. Problem.